materials, but also, you know, implantable materials among others, and everything in between. And so we'll you know, touch on certain aspects of that as we go through this talk. But you know, I don't think any of this really needs to be kind of put in perspective right at the moment. But there are some short and some long-term implications of what of this whole COVID-19 experience, right? We're basically just talking about the, you know, the travel industry, right? I mean, that was travel for work, you know, whether you want to go to Stockholm or around the world, or there's some short-term implications of that. There's things on inflation, right? I mean, think of all this money that we're pumping into certain sectors, right? And we can talk about e-commerce or economic recovery or digitization. But what we're really going to focus on today is single-use plastics. Now, the utilization of single-use or short-term use masks has some big implication on trash, on recycling, on biodegradability, and we'll touch on a few of those. But yeah, right now it's an interesting time. It is a very difficult time with the pandemic, but it also offers some very interesting opportunities. So in these pandemic times, about half of people are recycling more. Now that's really interesting. A lot more people are paying attention to eco-friendly products. Sustainability and environmental issues are starting to become more important, right? And local community is more important than ever. Now, this one's really interesting because we can talk about like local, you know, why are we wearing a mask? Why are we, you know, not going out to parties every day? Not that I was doing that before but I feel like that might be the reason why I'm not going out to parties now. But a lot of this is kind of linked together. We want to do good things for the environment, for our local communities. And so overcoming those barriers to sustainability is very important. A lot of people are confused how to make something sustainable. They're not clear what sustainability means, and they don't really know some of the different terms. We're talking about biodegradability or organic or renewable. Like they all have slightly different meanings, some of which are regulated and some of which are not. You know, the classic example of this is organic. You know, your organic food. What does that mean? You know, did a lot of organic chemistry courses in my grad school. You know, organic and inorganic mean very different things, right? What does that mean for food? And so, tackling this concept of a mask involves all this. You kind of have to have perspective of some of this, because do people care? Do people want something that is biodegradable or not? And so, just to put this out there, wearing a mask is a very good way to prevent certain respiratory droplets from being transmitted. So, COVID-19, and we'll get to this more of how it's actually transmitted, but it is a very important method to prevent this the spread of COVID-19. Okay, so how are things spread? To be perfectly honest, back in March, Orlando and I actually live in the same little village around UBC. We weren't doing much because we figured, hey, this whole coronavirus thing is going to be over in 2 weeks, so we're just going to go on a few walks. We're not really going to have to do any work. So, you know, a few weeks into this, we were chatting, and actually, originally, I personally thought, well, we can't actually do anything with this virus because viruses are really, really small. And so capturing an individual virus is really difficult. But then we realized viruses are actually spread through water. So we exhale, as I'm doing this right now, right? I'm breathing out water, and those water droplets are much more controlled size. Okay, so here is relative size of different particles. From the human hair up here at 100 to 200 microns, all the way down to viruses, or virus down in the bottom left of the coronavirus is about 0.1 to 0.5 microns. It's about 0.3 most of the time. If you go up a few steps from that, you get to the respiratory droplets. okay, which are in the kind of micron to 10 microns kind of size, and then up from that, okay? But this is really important because capturing things in the kind of the submicron range is quite difficult. Once you get up into the multiple microns, it becomes much more possible with kind of simpler technology. It's not simple technology, but it's simpler than the technology that's required to, say, capture the Zika virus, which is very, very difficult. So we want to be able to understand the materials, characteristics, the physics that's involved with capturing those droplets. It happens in very kind of specific ways. We can think about interception, so it captures them. We can think about water droplets diffusing through a material, and so when I was out for a walk earlier, my mask actually became quite damp, and so diffusion becomes a little bit more important. You can think about impaction, so just hits the mask, or in certain masks, electrostatic attraction becomes very, very important. So that's just simply the attraction between negative and positive charges. So in general, the fibers are positive. The water droplets we breathe out are generally negative, and they attract one. And this is one of the aspects that some of the higher end masks use quite efficiently. Good. So we breathe out. I thought this was kind of neat. 100 feet per second. Yeah, this came from USA Today. Just found this today. But yeah, if you sneeze, you're sneezing at 100 feet per second. That's a heck of a sneeze, and it can go quite far, right? You see that for the most part, if you're just normally breathing, being within sort of 6 feet of somebody is fairly safe actually, because those water droplets are going to descend. It's not perfect, if you do sneeze, if you breathe upwards, right, you're going to change all of the physics of this involved, and it is going to be better to wear a mask even if you're within 6 feet. If you're outside, if you're beyond 6 feet or 2 meters, it is pretty safe. Okay. So when Orlando and I started walking around campus back in March, not really many masks, but when we started to get into April and beyond, started to notice a lot of masks littered around campus and around the city. So that was an interesting, well, not very nice, but interesting problem to try to deal with. So here's a part of our team here in the bottom left that did some of the initial work on this, and a whole bunch of pictures that Orlando actually took. It was entertaining to watch him. Every time there was a mask, he had to run over and take a picture of it. But we saw actually quite a few. Now, some of these are actually N95 masks. That was back in kind of April, but now they're more kind of surgical style masks. And so what is the implication of this? Well, yeah, it's littering the ground. Yes, they will kind of mechanically degrade over time, and that, you run a lawnmower over them. You're actually creating some microplastics, which can be problematic. But one of these polypropylene masks, so for example, here we have a surgical mask, not a terrible, great mask, like it's better than nothing, don't get me wrong. But the fit, which we'll talk about a little bit later, is not great. Usually made up of 3 different layers. You notice that those inner layers and that outer layer are big fibers. And that middle layer is usually electrospun or melt spun polypropylene fiber, which really does the kind of the most of the capturing that we're trying to do here. Okay, so those 3 layers together, that's what we talk about when we say 3-layer mask or a 5-layer mask. Those are three layers that allow us to use those aforementioned mechanisms of capture to take those water droplets out of the air. Okay, so we need something that works. We need something that mimics that what is out there already. So those 3-layer plastic masks, we can think of them as those single-use plastics. The problem really becomes in what's going to happen. We are talking about billions of masks, probably tens to hundreds of billions of masks that will be used just for the coronavirus. Okay, so any way you slice that, that is a whole heck of a lot of masks. And right now they're all being put in the trash. We can think about generally trying to recycle them. We can think about reusing polypropylene. It's not easy. Some of it is going to go to leakage, so into the oceans, into the forests. And the degradation times on polypropylene, polyethylene, we're talking about hundreds. Some people put it at 1,000 years, but I mean, we don't really know that for sure, but hundreds of years. So a lot of it's going into the landfill. Potentially some could be recycled, but the majority of it is just going to kind of go to waste. And that is problematic. Yeah, and one of the big things, at least here in Vancouver, is the litter that goes to the marine environment. Huge, patch of the Pacific is covered by a big trash heap. Unfortunately, we can talk about these fibers being broken down into microplastics. That's problematic also. And it's not just in the marine environment. We can talk about any rivers or lakes. What does that do? You know, if a turtle tries to eat one, for example, it's problematic. So what we want to use is a natural material. And since all of this started from a nice walk around campus, walk around through the forest, we thought about wood. Is it possible to extract the materials from a tree and use that for a mask? And so we're going to use a few of these components. We're going to talk about fibers. We're going to talk about lignin. Maybe in the future we'll use some hemicelluloses to make a biodegradable, compostable mask. Okay. So really what we want to be able to do is take that wood, we want to break it down into its component structure. We want to be able to structure it, and we want to be able to get those properties that are so important to be able to make that product. It is important. Each one of these is very, very important. The structure is very important. If we don't get that structure that mimics the existing fibers, we won't be able to capture those droplets. The properties are very important, and we'll come back to this at the end in terms of obviously being able to capture those droplets. But something has to be breathable too. We can block droplets very easily if you just take a piece of regular printer paper and put it over your face and seal it nicely. You'll stop the water droplets. You'll probably pass out in a minute or two, but you'll stop the water droplets. So, but it is a trickier thing to be able to have something breathable, so your air passes in and out, but takes out those water droplets. So fine tuning that is a tricky thing. So we really look to wood as inspiration. And Orlando, I know you're going to take over here in either this slide or the next. Is this the slide you want to take over, Orlando?
Any slide. It will be okay. Yes. So back to wood. Thank you, Johan. And thanks all for joining today. It's a big pleasure to share with you our story of the can mask, Canadian mask. And as Johan introduced, the idea here is to look for an alternative to non-biodegradable polymers. And of course, being surrounded by wood or by the forest, that would be the case of British Columbia, where the forest industry is so important. It made all the sense of the world that we consider the use of wood. And if you look at a piece of wood, it's really an amazing material that is given by nature and contains some biopolymers that are the most important in the biosphere. So again, it makes all the sense that we can use a renewable, sustainable resource to tackle a problem such as that of the securing PPE for everyday use. But this goes beyond PPE. We are thinking about wood not only to make paper, but to produce many different materials that can be quite advanced, from those that we use for packaging up to those that are related to optics, photoelectronic materials, and for energy harvesting. And this is what we do pretty much in the Bioproducts Institute, to look at the many possibilities of wood. And what you see here is a cross-section of a piece of wood, and you can appreciate the fibers that are long fibers or cells. They are hollow in the center, and they are surrounded by the cell wall that you can identify very clearly in this image. And those fibers will grow and will be a little bit different depending on the wood species, whether it's wood or non-wood species, or even on the season. So this is very interesting because some of these fibers can be finer, coarser, bulkier, and others maybe would be thinner. And that makes a huge difference, because if you think about a membrane for filtration, those type of properties are very important. So it's almost like in wood, we have materials that we can use by combining the different fibers to optimize the filtration efficiency. And just to put an example, in addition to the wood morphology, is the case of the wood pulp fibers that we can isolate from wood. So on the left, you can see what we call pulp. Is the fibers that you saw before, but after separation from wood. And on the left, those fibers contain another molecule called lignin. It's a polyaromatic molecule, and that gives this color to the wood pulp. But the main constituents is actually the fibers that you saw before, with a cell wall that contains the most important polymer in wood, and that polymer is called cellulose. And cellulose is a homopolymer, it's a linear polymer where the repeating unit is glucose. On the right is the same situation, but this is after removing from the fibers the lignin component. So we have unbleached and bleached fibers. And the beauty of these types of fibers is that they have different properties from the point of view of wetting behavior, from the point of view of the strength of the fibers, as well as, for instance, the flexibility. And by mixing those, you can fine-tune the properties of paper materials, as well as the membranes that we produce in our can masks. So let me talk a little bit deeper into this idea of going from wood to the fibers to cellulose especially. And I would like to share with you some ideas about fibers, micro and nanofibers. And we're going to go along, and we start here with the fibers. We talk a little bit about lignin, and at the very end, we jump to the end product, and that would be the fiber masks. But in this process, of course, we're looking into all these structure, property, product relationships that exist. And as you can imagine here, all this is linked from the beginning to the end, and it's very important, all the processing steps that are in the middle. So it sounds like it's a very simple material, and it is a simple material, but there is a lot of engineering behind it. So what you see here now is actually a piece of paper, and the fibers that you saw before in wood, now they look like flattened up, making the layer structure that we call paper. And these are the same fibers. They are, again, they are hollow, but they become like a ribbon as they collapse, because the lumen or the space in the middle is just replaced and just collapse during the process of paper making. And the idea here is, can we think about these fibers as making a network that we can use for filtration? And of course, for us, the main motivation, as Johan put it very well, is that we want for these materials to be able to biodegrade. And this is very typical from paper products. Paper products are fully biodegradable, and not only biodegradable, but next layer is compostable. And compostable means that the material degrades and then can allow for the material to decompose and sustain new life. The other component of paper and regular fibers is that they can be recycled. So here we have the two components, or the best components of the world, in the sense of a material that we would like to use, that goes back to nature, but can also be recycled if we wish. And paper making, of course, is a very well-known technique. What you see here is a paper machine. Sweden, and that we were talking earlier, also Finland and many other countries are known to have very advanced technologies in the area of paper making. And this is an example of a paper machine that operates about 70 kilometers per hour. Before I also heard about the space exploration and rockets or airplanes, for instance, from NASA, etc. And think about the following: these paper machines, the control system that is utilized in these paper machines are as advanced as what you will find in the most modern airplane. And these machines produce paper, and we want to produce something like paper that looks a little bit more like this. So this is a bulkier paper that has a lot of porosity, and this is what we proposed from the beginning to be used as the mask to stop the virus particles. And all this is based on cellulosic fibers. And I want to make a very small parenthesis about cellulosic fibers, just to very briefly comment on another cousin of wood fibers. And that will be a very special type of fibers that can be produced by microorganisms. So it's a different source of cellulose, but it's exactly the same cellulose that we find in wood. But in this case, it's produced by a bacteria, by a bacterium. And we call this bacterial cellulose. So the culture medium is the one that you see on the left, and in an aerobic process, a pellicle of cellulose is grown on the surface. That pellicle can be separated, and after washing, this is what you get. It's like a membrane. And this membrane under the SCM will look what you see on the right. So it's a very interesting possibility, at least to use these materials as a membrane for filtration. Of course, the cost structure will be quite different if you compare the fibers from wood compared to the fibrils that you produce from bacterial cellulose. Before we were talking about 70 kilometers per hour. Here we talk about a pellicle, like the one that you see in this image, that takes maybe 5 days to be produced. So completely different kinetics. But nevertheless, it's a very interesting concept because synthetic biology is becoming more and more important, and we can think about, in the future, using bioengineering and biofabrication to produce this type of mask completely locally. And that would be the case of these membranes that can be used for size exclusion to prevent the penetration of particles. And in fact, one beautiful aspect of these fibrils, same also for wood fibers, is that one can control the porosity. So this is an example of going from one very close membrane to one that is more open. So the same with paper, the same with the can masks that we made with wood fibers. We can control that porosity by given processes that we have implemented. So enough for the time being about cellulose in the two forms, wood-derived cellulose or bacterial-derived cellulose. Let me have a short stop now on another component that we consider in the can mask, and is the lignin that we talked earlier. So lignin is this brownish powder that you see here in this above this arrow. And that lignin I will show that can be converted also into fibers and particles. And before coming here to this talk, I learned that some of you were interested in listening a little bit about lignin. And then I decided to give a little the tour to talk about the possibilities for lignin. And lignin is a molecule that is also in wood. It's 1/3 of the weight of wood, so it's very important. It has a very high calorific value, and is what really gives most of the heat when you burn wood. And that means that really that's one of the main uses for lignin, just to burn it. But if you look at the literature, and there are some recent reviews that we wrote in collaboration with colleagues, it really becomes very clear that in the future, lignin needs to be valorized, and there are very important opportunities for lignin-derived materials. And they can be, very expensive type, low production by high-value materials, like those that can be used for UV protection, for emulsion stabilizers, or for carbon fibers. Or they can be very high volume that are produced from these lignins at very low value or cost, and that would be for biofuels. And somewhere in the middle, we can maybe find an opportunity for lignin in applications for making membranes. And those lignins can be produced in large quantities in typical pulp and paper mills, but there is something that is emerging very strongly. It's a concept of biorefineries. And from biorefineries in the future, there will be a very large volume of lignin available. So we are looking into new uses for lignins. And as you can see on the right, some of those are very relevant to the masks. That they can be used for coatings and antimicrobial applications, and also for membranes for given properties. So I will just highlight 2 or 3 of those. First, the lignin is a polymer that is not really linear, and that means that it's difficult to make fibers, but nevertheless, since long time ago, we and others have been engaged in the fabrication of lignin-based fibers as a replacement for carbon fibers. And this is possible by typically 2 important techniques. One is electrospinning, and the other one is solution blowing. And here in Bioproducts Institute, we are acquiring an electrospinning unit of about 1 meter width to make this something more scalable. But solution blowing is even better. And what you see on the right is the type of process that is used to take a lignin solution and produce fibers. Now, the difference with cellulose is that in cellulose, the fibers are already made by nature. In the case of lignin, we need to put it together in such a way that we create the fibers. And we have been working extensively looking in this type of maps to find the conditions to make the best possible fiber webs based on lignin. And these are some examples of those webs that can be used for the purpose that we are discussing. So besides cellulose, lignin is a possibility, and we are exploring here in BPI with our colleagues opportunities for lignin-based membranes. The other opportunity for lignin, not as a fiber, but is to make particles. And in the center, you can see a design that we have. It's a material that looks like a spread dryer, but it's using an aerosol flow system that under laminar flow can take a lignin solution from industry, and using a heated tube and a stream of air, the droplets of liquid that is the lignin solution can become into particles like the ones that you see on the right. So it's a beautiful example of utilizing this molecule that you see now on the left. It's quite complex, but if you want to make fibers or particles, I think there are many opportunities. And one of the beauties of lignin is that depending on the source, you can adjust the wettability of those particles. So we call this the surface energy. We can make them wettable by water on the far left, or we can make them low surface energy. That means also more hydrophobic, more water repellent. And in the mask, this is something that we need to control, the repellency to water. For that, I show here an example of a coating that is produced with these lignin particles, and it's super hydrophobic. That means in this particular case that the contact angle with water is greater than 165 degrees, and the so-called tilt angle is 5 degrees. So it's a self-cleaning, super hydrophobic surface that is produced by coatings with the particles, like what you see on the left. That would be the cross-section of this coating material. But more important than that are the properties, not only of hydrophobization, but the properties that you can achieve with these lignin particles, and some examples are displayed on the right. Antioxidant activity, UV shielding activity, and anti-fouling. And as Johan will tell later, for instance, anti-fouling can be an important component in the fabrication of these masks. The other one is antimicrobial, and this is maybe a little bit complex slide, but with colleagues in North Carolina, we have been looking into the antimicrobial activity of lignin. And it's well known now that the use of lignin mixed with ionic silver produce the best antimicrobial material that is known, better than, for instance, the silver nanoparticles themselves. So I just keep the explanation of the details, but just to highlight that the lignin can be also used as an antimicrobial material. And finally, the lignins that I showed earlier to produce the electrospun webs by different techniques can also be used to produce microfibers, like by this technique that you see on top. Is called wet spinning. And in this case, what we do is we take a lignin solution, we add a little bit of a nanomaterial that is called cellulose nanofibers, and that combination really is an ideal combination to spin something that in a coagulation bath will become into a filament. And you can see this in operation on the far right here. This is a extruder, this is a coagulation bath, and that mixture that I just mentioned can be formed into filaments. So a huge opportunity for both cellulose and lignins when put in solution to make filaments that can be used for textiles. And this is exactly what you see on the left. Textile from wood. This is not for masks necessarily, but gives the idea that wood-derived materials are really becoming super important even in the area of textiles. And this is an example on the left of the use of a solvent, in this particular case, ionic liquids, to produce textile materials from either wood, from paper, recycled paper, and waste textile materials. And there are huge investments now, especially in Finland, where I was before, where these processes are considered. Okay, So back to the can mask, and now you realize that the utilization of cellulose fibers or lignin is quite important in the assembly. Now let's talk briefly about the filtration system that we want to produce. And of course, all this comes not for granted. There is a little bit of history here in the Bioproducts Institute and also in collaboration with other organizations from the past, where we have learned about techniques like wet laying and how to make these webs flame resistant or protein resistant. Johan discussed briefly about the electrostatic charging. All of this can be done or can be put together in making these membranes. And the video that you see on the right is a little bit of the process that we use. It's a wet laying unit where we put the fibers that I just mentioned, in this particular case, bleach fibers, and then they are laid down in a system to make a fabric or a membrane that will become the final mask. In this particular case, we're not using lignin, but this is the next step in our development. So my last slide before Johan takes again over. The idea here is that we were looking for this type of paper-like materials that you see here on the bottom right that are like a membrane. It is porous, and then they become the active component of the mask that are able to stop the more difficult particles, those in the range of 200 to 300 microns. And that active component can be surrounded by a passive part in the mask that is the largest area, but where we don't need this requirement of filtration efficiency. And for this, we prototype different approaches. We use different techniques for assembly, including 3D printing. And these are some of the molds that we use. And from there, I think, then we successfully produce different prototypes that now Johan will finish to explain, and also especially in the context of the functionalities that we were looking for these membranes. So Johan, over to you.
Great, thank you, Orlando. Back to that. Yeah, so there's, as Orlando was pointing out, you know, this is not simple. It uses simple components, but it is a complex way to put these together, right? I mean, in the simplest case, we are just using a chunk of wood, right, that we've deconstructed and reconstructed to make these foam-like materials. Like Orlando said, if you combine these kind of very refined nanomaterials, the nanocellulose, the nanofibers, the lignin together, you can get a filtration material that is about equivalent to the N95 standards, and we'll get to that. Oh, of course, I just opened my own. Second here. What's going on? So, what is important? Orlando touched on the components that we can use, but it is being able to combine those in a way that we can get to using the structuration and the properties of those materials to get to a few different things. I previously mentioned that we need breathability. Obviously, we have to be able to breathe through this mask, or you know, for anybody that wears glasses, once you have that mask on, you'll breathe and you'll fog up your glasses. Now that really means that your breath is not going through the mask completely. It's probably going around. So breathability is important. I'll tell you here in a couple slides, very important. Some of the other ones, depending on the application, are very important. These are all of the requirements for an N95 standard mask. So bacterial filtration has to remove bacteria. Okay, particulate filtration. So obviously water droplets, but also other dusts. Okay, fluid resistance. It actually has to be resistant to blood, and then flammability. Now, for most of us, most of these are probably not terribly important, right? I'm not sure how you guys deal with you know, going to save on foods, but generally I don't get any sparks on my mask, and I generally don't have any blood in my mask. You know, maybe if you're arguing over some toilet paper, but not these days. We're past the toilet paper fight stages. But to be able to get these into a medical environment, we need to be able to meet all these. For consumer product, probably the breathability and the filtration is enough, but we do want to meet all of those standards and exceed those standards. So does it work? Does the mask that you currently use work? Well, if you took a piece of plastic, just a plastic bag, for example, and tried to breathe through it, you can't breathe through it, right? It doesn't, it has very, very low breathability. In the beginning stages of COVID, we had a lot of surgical masks that didn't work. When you put them on, it felt like you're breathing through plastic, and all of the breath went around the mask. That doesn't really help. What we really want is a high breathability system, like on the right, but that removes the water droplets. So we're looking at that 0.3 micron and above water droplets to remove, and so that we can reduce the spread of our COVID. Like I said, very important to be able to breathe through the mask. This was some interesting work over the summer that we did with some students. So these were undergrad students that we took as summer students, and they modeled the mask. They basically took different scenarios. So you can actually get a iPhone app, and you can scan your own face. So this is one of the students' faces. And he was able to scan his face and then fit a mask on there and see the different breathability as a function of the fit, basically where the air went. If it doesn't fit, the air goes around it. Depending on how breathable that material is, well, if you breathe out, it can still go around it, even if it is slightly breathable. So very important, and it really spoke to well, the interest of students, the awesome work that they could do in terms of modeling, that way beyond both me and Orlando, and to be able to look at these different things. So the wearability, the filtration efficiency, all with an eye on that biodegradability. So in our very first generation of masks, this is months old now. But on the x-axis here, we have different types of pulp, so different types of fibers that we're incorporating in here. And just by changing the type of fiber, being able to form that material into a foam that we can breathe through, we can really alter the filtration efficiency. So we're comparing to 3 different things here. In green, that N95 standard, very, very high, and really the gold standard right now. The surgical mask, which is somewhere between 92 and below. A lot of those masks you're going to buy at the store are probably going to be more at the 60 range, but we were optimistic with this. And then the cloth masks, so this is the 3-layer cloth masks, will be around 50 or 60%, but still very good. So by altering the type of fiber we use in this foam forming process, we can get anywhere between 10%, which is very, very breathable, but not very useful, all the way up to 90% or 85 or 90%. And this is in the first generation. So we've refined this, and this is a single layer material. Okay, so with 1 layer of our very good filtration material, we can get to the standards that are met by those 3-layer cloth masks or the 3-layer surgical masks. So we think we've got a really good handle on this, and we can do some really neat things with it. Back in the summer, we were able to present this to a few different people. Hopefully, you'll recognize that guy in the top in the middle. We pitched this. He had some fantastic questions. Asked about the hydrophobicity of this masks, which was what Orlando's points about lignin really dealt with. The other thing he asked about was, well, what about the other components of the masks, the compostability or the biodegradability of, say, the band? Well, we've come up with a solution of that. We can make materials that are tieable and a little bit stretchable. One of the trickier ones is actually the bridge, the piece of metal that goes over the bridge of your nose. That's traditionally done with metal. But these days we can actually do it with a flexible plastic. So it certainly is possible to do this all with biodegradable materials. So have a truly biodegradable mask that's either biodegradable and or compostable, filtration efficient enough to be able to use for short periods of time. Really, we're trying to design this to be able to be used for hours, not days. Okay. And so now we're up up to the point of investigating prototyping and production. Oh, so prototype. Sorry, now we're into looking at production. This is a traditional. This is a 4-layer line that's actually just across the street here at UBC, combining 4 different layers into a clam style mask that works very well. So you can combine potentially 4 different layers and make masks kind of in the 5 to 10,000 masks a day per line, I think, for this. Okay. So really, we're now trying to get through all of the legal matters of combining with a company that can really take this and push this into the market. So with that, I mean, I know we left a couple hooks in there. We left a couple open questions, and we'd like to thank you for joining us. Both Orlando and I really, value these opportunities to kind of present to all sorts, right? And so, yeah, thank you for joining us, and we're more than willing to take any questions.
Will I watch that interview with Melanie?
Yeah, we can't hear you.
I just unmuted everybody, so I guess we could just ask the questions by voice and video. I hope this works. If not, then we'll go back to the webinar.
It'll just be challenging if there's feedback, I guess, or cats crying.
Okay,
So,
I guess.
Cassandra, raise her hand.
Hi. Hello.
Yes, hello, Cassandra.
Hello.
Go ahead.
My question is, how does the amorphous structure of the mass, or in general of the fibers, help with the filtration system and the bacterial infiltration system in comparison to an ordered structure, if any investigation has done on that?
So,
Yeah, go ahead, Orlando.
So if I understood correctly, how the structure of the material helps in the function, right? Is that what you indicated, the structure, right? The relationship or the influence of the structure, right, Cassandra?
Yes.
So this is, of course, very interesting, and it seems to be very subtle, but it's actually very important. So the fiber type will have a huge difference. So for instance, fibers that contain more lignin, like the unbleached fibers that you saw before, they are generally more stiff. And that means that when you put those fibers together, they make a structure that is more open, less flexible, and more porous. If you use bleached fibers or chemically treated fibers from wood, they are usually more flexible and conformable, and that means that they make a structure that is less porous. So in other words, the porosity can be controlled by the fiber type, whether it's bleached or unbleached, or even the tree that you use, whether it's pine or cedar or eucalyptus. In Brazil, of course, eucalyptus is super important, right? So that makes a huge difference in the filtration efficiency. And one of the plots that Johan showed actually included a comparison for the 3 different types of fibers. He was using their chemical, thermomechanical pulp fibers compared to others. And you saw that the efficiency was completely different. So that speaks to the fact that the structure will influence very strongly the filtration efficiency. And it's a beautiful example how different fibers that we can harvest from nature or from different processes can get what we want, whether very open structures or very closed structures. And finally, those structures is another funny side story, is that that structure can be measured by the filtration efficiency, but there are other techniques that are very important in your area in material science. And that would be, for instance, light scattering. So by using light scattering, we can get a sense of that structure of the material, whether it is open or closed. The opacity of the material tells you a little bit about that as well. So very beautiful component of material science.
Forgive me if you already mentioned it, but what sort of material would you use for the actual keeping of the mask close to your face? What's the loops like for your ears and things? Is that also going to be? I mean, that's less need for of course, the porosity. But what kind of material would you use that would be biodegradable?
Johan is a world expert in that because I saw in his house some of these strands. So you can answer that, Johan.
I mean, in the simplest case, you could just use a cord, right? I mean, you think of hemp fibers or something like that. In the ideal case, what you want is actually something with a little bit of stretch because you want to be able to pull it back. Interestingly, that the N95 masks do not allow the behind the ear loops. They only allow the behind the head, actually. And so it's actually much easier to tie those. And so we use essentially a rolled fiber and a couple mixed types of fiber to give it a little bit of stretch. It's not as stretchy as the rubberized materials. And we can actually incorporate latex rubber, which is bio sourced, but not really biodegradable. So there's a few things.
Johan, since you are talking, maybe there is a question by Devanga about the cost for the end user of the masks. Maybe you have that better than me.
Yeah, so there's two questions about the cost and expensive to produce. Well, I mean, we've been doing this on the lab scale. It is really, we're not reinventing the wheel for the actual fabrication of the mask itself. So those lines you saw that combine multiple layers, that's what we're relying on to essentially punch out these masks. So the production itself is exactly the same. It needs to be fine-tuned slightly, but essentially the same as the, sorry, I had to mute somebody. I was getting too much feedback. Is essentially the same as the regular kind of higher end sort of sub N95 style mask or KN95 style masks. So that's half the question. The other question is the actual filtration material. And so a year and a half ago, I would have told you that it would have been very tough to kind of compete with the polypropylene spun fibers, which is, you know, the layer of the mask that really does the filtration. But now, you know, in the span of March to April of last year, it went from about $1,000 a ton to about $40,000 to $60,000 a ton. So when it's in that sort of range, it is we can make a very compelling case because we're shortening the supply chain. We're using local fibers, so there's a lot less transport. And the one of the big problems that happened last year was that getting a lot of that filtration material was very, very difficult.
I can take a question. The next question asks about the water consumption for the production of these materials, and to add to that, what would that be compared to typical disposable masks? So this is a super important question, and you know, as usually is the case, when you handle bio-based materials, usually you require a lot of volume of large volumes of water. So water is so important in all processing of fiber-based materials. So we need to use water. And in pulp production, paper making production, water is an essential element. Without water, there is nothing. So this is a challenge, right? Now, good thing is that in these processes, we have very closed loop water systems, meaning that we recycle a lot of the water at the industrial scale. And then in the larger picture, companies are equipped with the different filtration systems to recycle the water that is used and to put any excess back to the water bodies. And that includes desalination and membranes that are very advanced nowadays. But a nicer angle that we have played in this exercise that Johan and I have explained is that we are using something that is called foam forming. We didn't discuss that in detail, but the idea here is actually that we don't use only water, but we use air. So we replace water with air, and up to 70% of the water is replaced by air bubbles that are used in the process of wet laying. So that's an angle that we didn't describe, but it explains a little bit our idea of reducing the water consumption and at the same time producing a material that has a better bulk or more porous structure. And that's because the air bubbles that are used. So that's an angle that is quite important. Now, compared to disposable mask, in disposable mask, depending on the case, you may use water as well. In the disposable masks that are made from polypropylene, the way that they are assembled is very different. It's a different process that may use or may not use water. That depends on the process. The main issue with those polypropylene fibers, of course, is the fact that we're using a non-renewable material. And as we discussed at the beginning, the degradation really is prevented and is a big limitation as far as the production of microplastics. Finally, cotton is an example of another fiber that is beautiful, is very nice, but I have to tell something related to cotton compared to wood-based fibers. Both cotton and wood produce cellulose. It's the same polymer, but cotton has an issue as a crop. Cotton is a crop that really requires actually a lot of water for keep the crop producing, and also requires a lot of biocides, pesticides. It's a very not very sustainable type of exercise. For that reason, in the future, we think that replacing cotton with wood for textile materials, as I explained, is a very good alternative. That's one of the issues. The sustainability of the cotton is being more or less questioned, at least in their use. It's used to produce textile materials.
Yep, I'll handle the next question. Elizabeth asked about how do you test the filtration efficiency. It's a filtration efficiency tester. The basics behind it is that it aerosolizes salt water on one side and essentially detects on both sides to see how much of that aerosol is pushed through the mask. Very, very important what the size of that aerosol is and what the flow rate is. So we breathe at approximately 85 liters per minute, apparently. And so we test at roughly that rate also. So to make it comparable to kind of real life situations. A lot of the early work that was done was some very strange filtration efficiency testing. But they've since kind of standardized this to 85 liters a minute and the size of those water droplets. I'll handle the other question because Orlando kind of answered about half of it. You talked about extracting cellulose from wood. Did we look into other options such as cotton and hemp? To be honest, we didn't really look into cotton too much, just because of the implications that Orlando has said. Plus, we really wanted to stick to Canadian crops. That being said, we have hemp is a fantastic fiber. Kind of very different in some ways than wood. So we are looking into that for certain applications. Really, at the beginning of this project, we started with wood because we were pairing with some pulp and paper companies because we wanted to be able to do this at scale. But we are looking at other ones, and both Orlando and I have looked at cotton fibers or cotton-based materials in the past. It's just doing that at a huge scale is tougher. One other question from Anu. How do you balance the hydrophobicity in the mask? It's an interesting question. You know, if you've used a cloth mask, you've dealt with this problem already. In that cloth mask is not very hydrophobic or quite hydrophilic. In fact, it gets wetter, right? I mean, it gets moisture. That does change the filtration efficiency, and that's true for all of these. There are some simpler for wood fibers. There's some simple solutions to this. There's some fantastic paper chemistry essentially for adhering on hydrophobic compounds. Think waxes and things like this that are safe to use around the human body, but still provide enough hydrophobicity. hydrophobicity is one. The trickier one is actually the electret. That's much tougher. That might be left for things like Orlando's electrospun lignin or something like that, or other options.
I know you alluded to how long it would be a very temporary mask, maybe a day, you said. How is that to be measured? Because people are going to keep using, I mean, I see people reusing the same medical mask all the time.
I mean, in reality, we can't really control how long it's being used, right? And that's it's the interplay between the last three things we've kind of talked about, right? What the fiber is, how hydrophobic it is, and kind of how wet it gets as it relates to the degradability, right? The great thing about polypropylene is that it's very hydrophobic and it's very chemically resistant, which makes it not biodegradable, right? So you can't have something that's completely hydrophilic and won't degrade over in a shorter order, right? So there is that interplay there. We can't really control how long people, but you know, if the mask falls apart, okay, that's probably not good. But really, these are you should be using these masks for sort of hours, right? Like the truly disposable masks should be used in minutes to hours, not weeks to months, sort of thing, right? It's very different than the cloth masks. We could talk about the ins and outs of the cloth mask and how they change, but yeah, this is really for shorter term applications.
But in a way, that's good then, that it would degrade, because then you can't use it, which actually kind of helps control people a little bit.
And it is safer that way, right? In terms of like if you use it once and throw it away, there's a lot less risk of cross contamination. A question about the thickness of the filter. Well, we've gone anywhere from probably about a millimeter up to about a centimeter. Centimeter is a little too thick to have in your face. Again, it's this interplay between the breathability and the filtration efficiency. You want a thinner material because of the breathability. You don't want it too thin because it becomes problematic for some of the other features. In reality, you actually want 3 or more thin films together. That really gets you to the filtration efficiency, because the filtration efficiency that I put on that graph was for 1 layer, and so we were comparing apples and oranges by comparing to 3-layer materials before.
There is a question here about the moisture indicator, and this is a fascinating area. As we go deeper into the design of this mask, of course, many opportunities will come. And one of the big plus of using vegetable fibers or wood fibers is that they can be very easy to modify. Polypropylene, for instance, being so inert, is difficult to modify, relatively speaking. But cellulosic fibers are very easy to modify. And that means that you can change colors, you can print on it, you can also assemble in such a way that you can put indicators or sensors. And that will be the next level of development, right? So to create masks that can be able to transmit or communicate. And we have some projects related to that area, printing batteries, printing antennas on paper-like materials. This is something that is already being done in some research projects in Bioproducts Institute. In the case of masks, of course, that will add to the cost, but it's a possibility, adding indicators of humidity and sensors, actually. We can add sensors, print sensors, and antennas that can help to communicate. This is not far-fetched. This is something that is already around the corner.
Yeah, the moisture indicator is fairly straightforward to do for the science, but I would say then you have to seal the mask, right? Because if you live in Vancouver, your mask is going to is going to turn red right away. Right away. If you live in at the Yukon in the middle of winter, your mask will never turn red because it'll never have any moisture on it. So I mean, there's some tricky things. And then what are the implications of having to seal a mask in an airtight or watertight thing and then transport it that way? So it's a good idea. It's just a non-trivial to also implement at a large scale and have people use it in the appropriate way. Good.
Okay, if that's it for questions, I would love to unmute everybody and give you guys a round of applause, but would that be just too loud for your headphones? Or is that okay?
We can use the clap emoticon.
Go for it.
Okay.
Okay, or you can snap the fingers. I was on one of those Black Lives Matter calls, and that's what they were doing, and it made a lot more sense.
Well, thank you very much, everybody. It was very nice questions, and yeah, very nice to talk to everybody.
Yeah,
Excellent presentation, really interesting.
Thanks to all.
Great.
And good evening to everybody.
Go Canada.
Have a good evening, everybody.
Bye.
All right, bye.
Bye-bye.
Bye-bye.